It's a great pleasure to welcome online Professor Siram Ramakrishna, our plenary lecturer this morning, and also Professor Ipsa Roy, who will be giving a keynote lecture this morning. It's also a pleasure to welcome the President of the Polytechnic of Leiria, Professor Rui Pedrosa, who, although he's here in his capacity as President, I think he probably has a keen interest in the topic of this conference because he's a marine biotechnology by scientific direction. So it's there. So I want to say a few words of welcome and to explain how this works. So this is the International Conference on Advanced Research in Sustainability and okay, a little of the history. So we started with a conference on sustainability and international manufacturing in 2011 and in 2013, but in 2016, big changes in CDRSP because first of all, we moved to this marvelous building we're in at the moment. And later in that year, we held the first edition of this RESIM conference, which was 2016. It was also held in June, so a good time. In 2020, if you remember the heady days of 2020, when we could run around and not worry about masks and pandemics, at that time, we could see what was coming. And so we decided, not for reasons of the pandemic, but reasons to minimize the carbon footprint of the conference, to make it online, because it seems strange to us to organize a conference about sustainability and then require people to jet in from all over the world. And that was the first virtual conference we'd organized in the Center for Rapid and Sustainable Product Development. And it was a great success due to all of the help from people within CDRSP to make it smooth and work well. So thank you to them. Then we move on to 2022. So we're now on the third edition. We're maintaining the open science policy. So all are welcome online, in presence, at no cost. So this is part of an open science policy. So this year we decided to maintain the virtual element, but also to provide researchers close to CDRSP and at CDRSP the opportunity to attend in person. And of course, we can look forward 2 years' time to another conference of a similar style. So, some thanks. We thank the President of the Polytechnic of Leiria for his continued support. He was here at the first RESIM conference. He was here at the second RESIM conference and is here at the third RESIM conference. So thank you. We thank all of the plenary and keynote speakers for giving their time and support to this conference. We thank the hardworking technical team at CDRSP led by Renato. Thank you, Renato, and includes Andre, has disappeared, Artur, Fabio, Thomas, and somebody I've forgotten. But anyway, we thank you all. And also to thank the conference session chairs who will chair each of the half-day sessions as shown on the screen. It's a particular note to record that for a research centre, having international partnerships is very important. And it's with great pleasure that we can record that tomorrow morning, all of the keynote speakers will be given by people we have partnerships with or we will have partnerships with. So Dr. Manoj Patel on the left and Vijay Meena are both from the CSIR Central Scientific Instrument Organization, which I hope very soon, President, we will be signing the memorandum of understanding with them to start an international collaboration. And the person in the center is well known to many of us, is Professor Mahadevappa from Karnataka University, who we've been partners with since 2014, and with which we've organized the International Conference on Direct Digital Manufacturing and Polymers. So thanks to all of those three for contributing to this conference. It's a good start to new collaborations, and it's good to record. On the basis of collaboration, I holding the International Conference in Direct Digital Manufacturing and Polymers, which will be this time, it will be in India in 2021. It was here in Marina Grande, so it will be there. And we look forward to meeting some of the people who will be speaking at the conference. And it's also a pleasure to record that at the very first International Conference on Direct Digital Manufacturing and Polymers, Professor Seeram Ramakrishna was one of the plenary speakers at that conference, and he's been a friend of CDRSP since then. He's spoken at a RESIM conference and at one of the online ICD map conferences we've had. So he's well known to us. So thank you, Seeram. And so now it's my pleasure to invite Professor Pedrosa to say a few words of welcome.
Good morning to everyone. It's a great pleasure to be here on the third RESIM conference. Of course, I want to greet all the people that are here in a presential way, in a face-to-face, which is also very, very good to have these kind of moments that we are together. Of course, in terms of sustainability, is not the same when we look to the possibilities to collaborate with people that came from all over the world, but it's a good compromise to have this hybrid strategy, to have people that are here in the CDRSP and people that are online. I want to also welcome and greet all the people that follow us in an online point of view. Of course, I want to greet all the directors of CDRSP, Nuno Alves, Artur Mateus, the chair of this, one of the chairs of this conference, Professor Mitchell. It's a huge pleasure to be here, and the work that the CDRSP are doing related with the sustainability are amazing. I want to thanks as well. I want to thanks to the organizing committee. I want to thanks to all the chairs. I want to thanks to all the researchers and staff of the CDRSP, and I want to thanks to all the keynote speakers that accepted to be here sharing knowledge with and to the world, because this is, as Professor Mitchell said, is an open science conference, because it's completely open to share outstanding researchers that go for all the world. I also want to thanks all the researchers that submitted research works to share during this conference, and I want to emphasize two or three things that are very important and completely critical for the sustainability in a global point of view. First of all, the conference has a completely alignment with the sustainable development goals, but also when we look to the Polytechnic de Leiria strategy, this conference is completely connected with our green transforming agenda, but not only with our green transforming agenda, but also with some main principles and guidelines that we have in the regional university network, which is a European university led by the Polytechnic of Leiria, including for the construction of an European innovation hub related with the future industry and the regional sustainable development. I also want to say that for this region and for Portugal and for Europe, the thematic issues that you will discuss during the conference, namely manufacturing and climate change, because this is a focus conference on sustainably related with manufacturing processes, but also the manufacturing for secure societies, the manufacturing with innovative sustainable materials, the manufacturing for improved health and well-being, manufacturing to enhance food security and bioeconomy, the intelligent manufacturing systems that are completely connected with Industry 4.0. What I want to say is that we are in a transforming process related with the way that the industries in Europe are working nowadays. This region is a very innovative and productive region that completely needs as well to improve the process and the way that develop products. And this conference completely give some roots for this transformation of the industry of the future. And for me, as president of the Polytechnic of Leiria, as well for the region is very, very important. Finally, I want to mention that we still are in the with a pandemic condition. We are now, fortunately, we are here without masks, which is very good. The impact of the pandemic situation are not so bad nowadays when compared with last year or 2 years ago, fortunately. But in fact, we came from 2.5 years in the pandemic condition. We have a war in Europe, and these two things completely demonstrated that we need to invest more in science, more in support a society through the knowledge. We need to invest more and more in innovative process, in sustainability process, because the main societal changes are completely global, and we need scientific international networks. We need to have open science together in international networks to try to overpass this huge challenge that we have in our society. So this RESIM, the third edition of RESIMs, completely are in line with this idea. The main global challenges are global, but to overpass them, we need to connect the researchers, the teachers, the companies in the world for together overpass this kind of challenges. So thank you very much to be here during these days to share knowledge with the world. It's an honor for the Polytechnic of Leiria to have this conference in our house, and it's also an honor for me to be here to open this conference. Thank you very much, and enjoy and share the knowledge that you will have during these days. Thank you.
Thank you very much. I forgot to congratulate you on the award of the Sustainable Award for the Polytechnic campuses.
Yeah, it was. Thank you very much.
Renato, you can unshare. Yes. Management of the Polytechnic beckons, I feel. Okay, right. So thank you to the President for those warm words. And now we can start with the first session. And it's a great pleasure and a huge honor to introduce Professor Sriram Ramakrishna, who is from the National University of Singapore. He is well known to many of us, but for those who don't know him, he is one of the most influential minds in the world, not in Singapore, in the world. And he investigates a whole variety of problems. Today, he's going to be talking about the circular economy. But I noticed while searching on the internet yesterday that he has an online lecture which is about aging. So if you're in the older spectrum, maybe something useful to watch. So today he's going to talk about net zero and circular economy shaping the future, the role of materials, is very central to us here at CRSP. So welcome, Sriram, and over to you.
Thank you, Jeff. Can you see my screen?
Yes.
Okay, I will make it as a slideshow. Okay. Are you able to see the screen now?
Yes, yes.
Okay. Thank you very much. Let me begin my lecture congratulating the university for winning the award. I just heard through the inaugural opening speech of the president, Louis. That is always a pleasure, and I never be able to say no to my good friend Geoff. He remembers me and invites me for these important conferences he holds regularly. As he said, I'm a cross-disciplinary researcher with an interest in nanotechnology applying to diverse fields. Today, my focus is to discuss the role of net zero circular economy shaping the future with the lens of materials. As a material scientist, I use the lens of materials. As some of the information given, I'm quite actively involved in the space of circular economy in Singapore as well as the rest of the world. I like to echo that Geoff Mitchell has organized and put together stellar speakers. I'm delighted that I'm one of the many good speakers that have been lined up for this important topic on sustainability. I know some of you are not familiar with Singapore. Let me take a few minutes, introduce Singapore, our university, and then go on to the topic. I have already shared my slides deck through the chat box. Those who are attending this particular conference in person or via online, you could download a copy and it's available. So that's a skyline of Singapore. It's as beautiful as Portugal. And those of you like to visit, make sure you do visit Singapore in the future. That's a university where I'm working now as a senior professor. It's a university very well known, and it's among the top 10 in the world in 16 different subjects, and various subjects are listed there. And it has a number of highly cited researchers. Right now, we have close to 32 highly cited researchers in the world. It's a research-intensive university, recognized as the #1 in Asia, and has a strong research culture across the university. So, since we are strongly featured on various international rankings, it benefits our students. And you could see just a week ago, UK government announced our university graduates could go to UK for jobs. Similarly, the UK graduates can come to Singapore for jobs. So in a way, it explains how this global recognition sometimes helps the students. So now I dive into the topic, which is net zero and circular economy. First, I focus on net zero. Later on, I focus on circular economy. So net zero is about total carbon emissions to the atmosphere and concerns for the health of planet Earth and its ability to provide resources to the growing consumption worldwide. So this debate started nearly 50 years ago, what we call Club of Rome. That was 50 years ago, eminent people from around the world met and discussed, are there limits for the growth on planet Earth? And it's very clear in the last 5 decades, such a discussion is intensifying, and that translated into clear commitments by the countries. Even Portugal has declared it would be carbon neutral by 2050. So not only Portugal, more than 100 countries around the world, including Singapore, declared they would be carbon neutral by 2050. Similarly, major companies are also pledged to be carbon neutral. If you are not familiar with carbon neutral, it essentially means the total carbon emissions by a country or by an organization would not disturb the climate, and they would be net zero. And they like to achieve such a goal by 2050. Now, such goals also call for closer scrutiny of the announcements by the governments as well as the companies. Here is an example of HSBC. UK watchdog flagged them. Today I read the newspaper, Deutsche Bank CEO has to resign because of the greenwashing. So how do you avoid greenwashing? These are the steps one could do. If you are interested, it's an article I wrote about 3 months ago. It's available online. You could check it at that particular URL. Now come to the circular economy, primarily focusing on materials and materials linked to the carbon emissions. So 23% of the global emissions are related to the materials and production. And the consumption of materials by the world human population is steadily exponentially growing compared to 1970. Now we extract 3 times the resources from the planet. And if that particular trajectory continues in the next 40 years, it is unlikely planet Earth is able to sustain and provide the resources. That's the reason circular economy is strongly pushed by the scholars around the world. The best example is at the Nairobi meeting of the United Nations 2 months ago. More than 100 countries agreed that they will pledge towards limiting the production of materials, primarily polymers, in the coming decades. So they will be signing an agreement in 2024, which is 2 years away from now. So that is because material production is linked to the carbon emissions, also linked to the waste generation, which is affecting the health of planet Earth as well as human beings. That's the reason it is considered very important. If such circular economy measures are adopted, most likely we will reduce the carbon footprint through the circular economy approaches. And if the world does a good job, one could imagine such a trajectory of resources, supply and demand. So if you are interested, that's a definition of linear economy, which is pursued by the humanity for the past 200 years since the Industrial Revolution. But going forward, the emphasis is on circular economy, which is described in the top half of the slide. And this is the definition taken from ISO 59020, which we are now drafting. I'm a member of the drafting committee. This particular standard is now in the final stage. It would be circulated to all the countries so that it would be accepted by end of the year. So it's a new framework which enables the companies, organizations, as well as countries to measure circularity. So it describes the framework, the parameters, methodology, how one should measure circularity of the product or processes or organization or a country. So circular economy discussion has been around for some time, nearly 100 years, but right now it is much more stronger and much more sharper because of the worldwide attention on the climate change, global warming, which most countries are experiencing nowadays. So in a simple terms, regarding the Ellen MacArthur Foundation, they describe simply in 3 potential interesting ways. One could go over circular economy. You design out waste and pollution, keep products and materials in use as long as possible, and you find ways and means to regenerate natural systems. So I know Jeffrey Mitchell, as well as other colleagues at the center in Portugal, you are in product design and manufacturing. Obviously, circular economy principles and sustainability are very important as you design the products and also enable people to use the products and also manage the end of life of the products. So best way is to give you an example. I like this example, a Swiss-made watch. They claim 99% of the materials used in this watch are recycled materials. Now we all know that watch, even though it appears simple and most widely used, it has a large number of materials and also quite a complex construction. So manufacturing a watch completely out of recycled materials is a clear example of how humanity can adopt circular economy deeply, more ubiquitously, should we innovate and continue to innovate. So according to McKinsey, they say that there's a lot of investments is going to happen, and they expect more than a few $1 trillion investments will be made around the world in several sectors so that we'll achieve the goal of carbon neutrality and circular economy. The current geopolitics as well as the sustainability are becoming key drivers in coming out of the COVID-19 and future growth opportunities in Singapore as well as the rest of the world, which I'm observing for the past 2 years. So again, if you are a researcher and then you are considering, is it real? Well, these are the publications in circular economy. If you look at the keywords, this topic is trending very high. I myself have a journal now called Material Circular Economy, where I'm a chief editor. You are welcome to look at the journal as well as other opportunities to publish your papers. So it's an area that is gaining a lot of traction worldwide. So now I would go towards illustrating net zero circular economy principles using 3 areas: textiles, food, and housing, because these are very important for every human being on the planet. So, but I have lots of slides. Since the time is limited, I would go faster with these examples, but you have an idea how circular economy, net zero concepts are shaping products like textiles, food, and housing. So here is an example of textiles. In Singapore, less than 4% of textiles and plastics are recycled. Majority of them are ended up in incineration and landfills. So this is a story around the world. So more needs to be done in solving the problem. So if you look at the worldwide textile sector, the consumption of textiles worldwide is actually increasing last 50 years. And these are the major materials that are used in textiles. And textiles alone contributes to the, would say, second most polluting industry and contributes to 10% of the global carbon emissions. And again, as I said, worldwide, very less amount of textiles are recycled. Bulk of them are either incinerated or landfill. So why is this happening? That's because it's called fast fashion, which is trending worldwide. And if you like to see, focus on a blue bar on the left infographic. That's about China. And not the blue bar, sorry, that should be the China, should be the dark maroon bar. 20 years ago in China, when people buy a garment, they use it more than 200 times. 20 years later, they're only using it 60 times, whereas equivalent in USA is about 40 times, and European Union is about 100 times. So in other words, if you follow this trend in the future, fast fashion makes people to buy more and dispose more. which is causing substantial increase in the waste generation. And the right side is an example of Zara. I'm sure you are familiar with a company called Zara, but there are like many other companies like H&M and others. So if you look at this particular information in a typical textile production, you can see who are the major players and which part of the value chain of the textile. In a fiber production, China and India, whereas if you look at the consumption, Europe, North America are the major places. And the same could be analyzed from the different manufacturing steps. And you could see fiber production to the assembly, to the bleaching and dyeing and the consumption. So that's typically what happens. And now if you look at what is causing and which countries are experiencing carbon emissions and the waste generation and pollution, you could see in agricultural sector, China, whereas if it is cotton-based, that would be China, India, Pakistan. Wood is USA, Russia, Brazil, and Sweden. When it comes to the textile manufacturing, then trimming processes and retail and distribution, the scenario changes. So in other words, by looking at the total value chain of a textile, you would have a different answers and different roles. Different countries are playing and they are subject to different kinds of pollution, carbon emissions, as well as the solid waste generation. So this is basically what's happening. And now life cycle assessment tools are available. What one could easily analyze the impact in terms of carbon emissions, energy consumption, resource consumption, water consumption, as well as the waste generation of a particular product can be analyzed. In this case, is a t-shirt and a jeans. So we could analyze also which material system would be contributing to the large amount of impact on the environment. So those are the details. And now I go towards the total process involving, say, cotton or polyester. And this is typically what happens in the manufacturing. So it ends up in a landfill. So research is going on a lot in terms of recycling. And in this case, mechanical recycling is very common, most widely adopted. But moving forward, there will be more emphasis on chemical recycling and biological recycling. So if we're looking at how to get involved in a product design and manufacturing, you would be looking at the end-of-life solutions as well. So these are more details to convince you, as a lot of actions are happening in this area. So these are a certification of activities at the different stages of textile manufacturing. So what is interesting is there are new laws and regulations that are coming in place. I'm very sure Portugal has their own laws. In this case is France I'm illustrating. France is known for fashion. On the right side, the infographic presented says France adopted a new policy by 31st December 2021. It is illegal to dispose of unused fast fashion products. So in other words, all the manufacturers, the distributors are now looking at how do they rejig their supply chain and value chain and look at the total life cycle of a product. So there also another scheme called Extended Producer Responsibility Scheme. In Singapore, we adopted it. I'm advisor to the Singapore government on that particular scheme. This is very important to improve the recycling of plastics, electronic waste, textiles, and so on. So I'm very sure other countries like Portugal also have similar policies. So that brings us to what are the alternatives. There's a lot of research is now going on biopolymers or bio-based polymers so that their mechanical, physical properties could be enhanced and match towards the conventional plastics, which are fossil fuel derived. And how do you process and make them affordable is where a lot of efforts are happening. So these are more details. And if you are really interested, you should look at what is driving such a change in your own country. If you look at the extended producer responsibility scheme, you would know that the policymakers are driving the industry to change and adopt a better circular economy principles as well as a better sustainability reporting. So in fact, ESG reporting is expected in all the listed companies. Singapore, London, New York, they already have this particular requirement. It's called ESG reporting, environmental social governance reporting. So if you are running a company, you would be familiar with the process. So this is more details how one could look at. Here is an example. Adidas claims their products have a lower carbon footprint now compared to what they were selling a few years ago. So again, that gives you a company as large as Adidas is switching towards sustainable products. And these are more details. And I would not go into the detail, but these are the research we are doing in improving the sustainability of the textiles and fibers. These are more details. Whoever is interested, they could look at my slide deck. It can be downloaded from the link, the Dropbox link I shared with you. Okay. And so here is an example where we work with a South African small and medium enterprises and NGOs in making available women-related sustainable products. It's a very successful product in South Africa. And that has helped many women in South Africa. Okay. So now I move on from plastics to a slightly different example, so that okay, these are more examples from Singapore. Okay, now I want to show you in the food sector. In food sector alone, for example, we all drink coffee, and then coffee waste is now finding its way into as a flame retardant in plastics. That's an example how one look at the food waste into the upcycling into the polymer composites and high performance applications. Here is an example of a flame retardant applications of coffee ground after it is used. And similarly, tablets, medicinal product supplements, in this case, agricultural waste converted into this kind of medicinal products. In this case, our researchers are looking into the fat trappers using cellulose fibers from the waste, from, in this case, sugarcane bagasse and coffee grounds. So I'm very sure other researchers elsewhere are doing more such good work. And these are examples of waste, food waste, how it is valorized. And this is an example of a company in Singapore looking at the food waste in Singapore. And that's the amount of impact they are contributing into the Singapore food waste economy. There's also other activity that's happening. There is an increasing concern associated with the greenhouse gas emissions associated with the meat. Most people now have in their diet meat, and that contributes to a large amount of greenhouse gas emissions. There is lab-grown meat, or what they call synthetic meat, is finding its way to the dining plates. And in Singapore, as well as USA and European countries, you already find synthetic meat or lab-grown meat in the dining, for dining. And idea of this particular focus is synthetic meat has a less global carbon footprint compared to the meat harvested from the animals. So obviously that's a direction where a lot of research as well as the industrial activity is happening. So these are more details how digital technology is adopted into the food manufacturing sector. So there are several ways digital technologies are adopted. And in India, where I'm visiting next week, the Prime Minister of India has announced nano urea, which is basically a fertilizer. The idea is to improve the yield while reducing the consumption of the fertilizer. So now I move to the housing sector, and this is an analysis where if we have a circular economy concepts, you could reduce the total greenhouse gas emissions associated with the construction sector. So with a simple improvement of the material efficiency, you could save a large amount of emissions. The left side is about European countries, G7 countries. On the right side is China and India. So you could see the impact. So World Building Council, where Singapore is part of, there's a large emphasis on how do you reduce the emissions associated with the building sector. And these are the more details, and these are the innovations Singapore is doing in terms of improving the emission profile of the buildings and construction sector. It's an interesting point for some of the attendees and participants. We tend to use materials based on the mechanical properties, cost, and the physical properties. But moving forward, we also have to consider carbon intensity of the material. Here we are comparing carbon intensity of different materials. Obviously, aluminum and steel has a higher carbon footprint compared to the materials like wood and other commonly used materials by the previous civilizations. So there is an interest now in several countries to use wood in secondary structural applications, as well as probably the primary structural applications in the future. So there's a lot of research is happening. How do we use wood and repurpose wood so that we don't have to rely heavily on materials like steel and aluminum and concrete. So because wood is seen as a much more sustainable compared to those material systems and has a better carbon intensity. So this is how we design, for example, a data centers. We have a large research project worth close to $30 million with the Meta, which is basically formerly known as Facebook. We are actually building a green data center using nanotechnology. That's where I come in. We apply nanotechnology to improve the energy efficiency of the data centers. So again, Singapore is one of the key data center market in Asia, as well as in the world. We're number 3 in the world in terms of the data centers. A conference like this would not happen without support from the data centers, because data centers provide the storage of information and facilitate our communications. Obviously, hyperscale data centers consume lots of energy, and making them more energy efficient is the direction. That's why sustainability concepts are going into the future data centers. So these are some of the examples in building future living spaces in Singapore. And of course, we promote this quite actively. So moving forward, there would be a lot more emphasis on sustainable packaging. That's happening. There would be more jobs, according to some of the global think tanks. And 2 weeks ago, I was in Barcelona releasing the UNESCO report. It's called Knowledge-Driven Actions, Transforming Higher Education for Global Sustainability. The objective of this particular report is to emphasize the university education should be further changed and aligned with the United Nations 17 Sustainable Developmental Goals. It's a 100-page report. It's available freely. You are encouraged to download a copy and see how that can be implemented at your own universities. So this is a meeting we attended in Barcelona 2 weeks ago. And the more details, digital technologies are playing a huge role. in our transformation to sustainability. And for example, EU is planning now for the digital product passport. That means products that are sold in the European market requires a lot more sustainability data. And that means you need to harness digital technologies. I know the center in Portugal, you have a lot of digital technologies in manufacturing. You are in the right direction to think about how a future digital product passport contains information on the manufacturing as well. So here is a camera looking at automated systems, sorting systems. Based on that, one could automatically sort waste, textile waste, and an automated system would look like that. So this is the future potential. So in other words, a lot more nanotechnology, digitalization, automation will go into the sustainability aspects of materials and products in the future. So these are more details. And now I just want to end my presentation by saying I'm a strong believer in circular economy. That's primarily because I'm a material scientist. And I see a very close relation between future materials, sustainability thinking, so that we can reduce the emissions, we can reduce the waste, we can make the planet much more healthy and helpful for the future generations. These are some of the books we have written in the last few years, and some of them received international recognition. And there are many other good books as well. You are welcome to dive into those books and find your own path and make a difference to the world of materials, manufacturing, and the society. Thank you very much.
Thank you very much, Serum, for an inspiring presentation. Perhaps I could just remark while people are thinking of questions or comments to make, that there are two strands to what Professor Ramakrishna said, one of which is about the technology and the science, and the other lesson to take away is how he uses his passion to communicate those ideas to other people. Because the scientists, there's no point just coming up with a bit of technology. We need to infuse and engage with other people so they participate. And so I think we see the master of both the science and technology and what I think in old-fashioned language we used to call communication, but probably there's another word for it now, in both. So it's easy for us to ask questions in the presidential session because I can see everybody. Renato, perhaps you could identify if there's some questions online. So questions in the room? Artur. So Artur Matthias from CDRSP.
Okay, thank you for your excellent and very good presentation. Regarding sustainability and look into the, for instance, for the more specific zone, plastic side, how do you see now the pressing that for using bioplastics, plastics that came from nature? How do we deal with this, with that pressing? Because it seems that everyone wants to go in that direction, but perhaps we don't have so much land from where we get those plastics. How do you see that, please?
Thank you, Renato. You're spot on. There's a tremendous push on bioplastics because fossil fuel derived plastics have been vilified, especially single-use plastics. Many countries started banning single-use plastics, and that put a pressure on the worldwide manufacturers to look at bioplastics, and one need to look at bioplastics in a particular way. There are challenges in terms of the cost. People argue through the economies of scale, probably the cost will go down and become competitive. Second aspect is most bioplastics, they do have certain interesting properties, physical as well as mechanical properties, but more research needs to be done so that they're able to provide a similar level of properties that are delivered by other fossil fuel derived plastics. So that is an area where more efforts need to be done in addition to driving down the cost. But if you're looking at the end of life solution, we might end up with a mixed bag scenario where a waste would contain fossil fuel derived plastics as well as bioplastics. That would make the recycling much more complex and much more difficult. So current recycling methods and technologies are not suited for that particular mix of waste. So again, more need to be done in that area, and the systems, recycling systems have to be trained to deal with such a mixed plastic waste. And finally, I believe one also need to understand a lot more through the scientific studies. If you have large quantities of bioplastic, which is known to degrade, compost in the nature, what kind of emissions are associated with it, what kind of effects on the biodiversity, as well as quality of the water, air, and soil need to be more thoroughly understood. And even how would that change the oceans, salinity, chemistry, flora and fauna. So all these things would become something to be investigated when large volumes of these materials are started being consumed. To give an idea, the world now consumes close to 600 million tons of plastics. So that's a large quantity. And I would imagine in the next 2 decades, that might reach 1 billion tons because the worldwide population is still growing, consumption is still increasing, it has not plateaued. So obviously, this becomes a very important challenge. And but its good news is I'm an optimist that human beings are creative and they have the ability to innovate and solve the problems once the problems are articulated well and understood well. I'm sure new research is happening. For example, even fossil fuel derived plastics, they're now beginning to think about circular plastics. That means intentionally they're making the plastics to be circular. That means one need not completely switch to the bioplastics. One could make the normal plastics to be more recyclable by introducing different chemistry. So there's a lot is going to happen in the coming decades.
Thank you very much.
Thank you. Please, if you could speak loudly because the microphone's here. Yes.
So I really like that you speak about the meat industry because I think it's also like not sustainable. And you spoke about being like meat grown in labs. Is that like gonna be sustainable to like feed the whole world population, or do we have to switch a bit to a more vegan or like vegetarian how do you call it? Diet.
Did you catch the question?
Yeah,
Yes.
I got the question. I got the question. Thank you. So basically, you're asking 2 aspects. One is this synthetic meat or lab-grown meat, how sustainable it is. The studies so far, what I find in the literature, these studies especially come from published good journals. They do say that carbon footprint or greenhouse gas emissions associated with the lab-grown meat is much lower than the meat harvested from the animals. So that's what the scientific studies so far indicating. But I think if we believe that and if we continue in that one, it has the potential to supply and meet all the demand of the worldwide population because manufacturability is very good. We already have a few companies in Singapore doing that. I'm aware of a few companies in Europe as well as US. The question is, does it have any effect on the nutritional value and a long-term health effects of the human beings as well as other aspects? I think that information is still not sufficiently available. I believe that any change in the processes, there may be further studies required to understand the exact influence on our human health. So that requires longitudinal studies. I'm sure that's what is going to happen in the coming years. Now, your question is, should we all become vegetarian? Well, I think if you have this option, it is giving a midway option where you could still eat the meat. At the same time, you could be less worried about contributing to the emissions and impacting the health of planet Earth. So I guess this might be a solution for some people. But again, the worldwide humanity is a distribution. Different people would choose different choices. So I guess overall, I think we're still in the right direction.
Okay, thank you. Right, another question from the room here, Thomas.
Thank you. Thank you for your presentation. Focusing on the construction sector, on the sustainability of the construction sector, you talked a little bit about housing. Where do you think the higher gains in terms of sustainability will come from? Will it be from developing new materials, try to find new sustainable materials that incorporate more recyclable, let's say, waste streams or some of the kind? Or do you think that also the construction process and the construction technology will take a part there, and we must think of how we construct the buildings, how do you build them, and how do you arrange the materials that you have at hand at the moment? Where do you think the trend in terms of sustainability in the construction sector will be? Thank you.
Yeah, thank you, Thomas. I like to basically say it from this way. Construction building sector has two kinds of lenses. One is what we call operational carbon, another is embedded carbon. So operational carbon primarily depends on how efficiently we use the buildings. So worldwide, enough attention has been given in terms of the energy envelope of the buildings. So they have done quite a bit of progress. And at least in high-income countries, plenty of examples where buildings are designed and operated in such a way they are almost what they call carbon neutral and even energy plus. So moving forward, I actually think a lot more innovation is needed on the embodied carbon, which means materials and manufacturing. And there is a huge amount of efforts are needed. And that's where the next level of gains will be. In other words, we have to reimagine the materials. We have to reimagine the production processes. We have to redesign the way we design the buildings and assemble them so that they're ready for disassembly and future repurposing at the end of the life. So that's where I believe a lot more creativity and innovations are needed. In short, materials, manufacturing, and assembly, where we need to reimagine and redesign things so to have a much more benefits in the building and construction sector.
Thank you.
If I could make just a small comment, I saw last week some news that researchers in Cambridge have developed a zero carbon footprint way of producing cement by combining it with steel making. And I think that illustrates the imagination that's required to develop new materials and new manufacturing processes for generating materials. We can't think about the materials in isolation. We have to think about how we generate the materials and how we could perhaps combine generating several materials at the same time. Okay, other questions? Okay, if I could just ask the last question. One of the things that's I think that sets out the zero waste, the zero carbon footprint technology from other technologies is that this requires the partnership with society, because we're all players in this. We're all required to do something. It's not just the big companies. It's the people who are collecting the waste, the people who are separating the waste, and all of those things. And I wondered if you had any experience from your activities in Singapore about how you engaged with the communities to get them on side to help deliver the technology that's required.
Thank you, Jeff. You really hit the nail on the head. Real transformation only happens provided the people come on board, because people are the users of the product, and they are the one will finally pay for any changes in the cost. So everything at the end of it will be transferred to the people, because that's where the money is actually paid for the products and services. So consumer behavior adaptability is extremely important for the world to progress and improve upon sustainability and circular economy. In Singapore, how do we do it? My own experience. That's why you find me a typical professor spending a lot more time in communication. So my suggestion is we do a lot of interesting work in universities and labs and in our own minds, but most of the language we use and how we communicate is far removed from the common man, common person. And so scientists need to learn and feel comfortable to communicate to the public as often as they could. And that means writing articles, appearing in the newspapers, television stations, using various platforms like LinkedIn as well as other platforms. Of course, we had to be as truthful as to our knowledge, but only question is how do we communicate in a simpler way without compromising on the deeper aspects. So I think it's something we are not naturally trained, because scientists are different, researchers are different compared to the others in terms of the way we communicate. So you brought up the very important aspect is the communication is the way forward.
Yes. Thank you very much. So I think, unfortunately, our time is drawn to an end. So thank you very much for joining us this morning. We've all learned a lot about many different things, and we all look forward to maybe the opportunity to meet you in person again sometime in the not too distant future.
Thank you.
Thank you very much. And because now we move on to a lecture which is about biomaterials. So thank you.
Thank you.
Right, the next presentation is a change. Sorry. The next presentation is focused onto sustainable biomaterials produced by bacterial origin and their use in biomedical and environmental applications. And the keynote speaker is Professor Ipsita Roy, who's from the Materials Department in the University of Sheffield. This is one of the largest material science departments in the UK. And she's been very much a pioneer of the development of this type of biomaterials, stretching back to the time when she was a professor at the University of Westminster. So it's a great pleasure to welcome Professor Roy to the stage, and over to you.
Thank you.
Okay.
Hello, can you hear me?
Yes, yes.
Great, thank you, Professor Mitchell. Great to be invited to this fantastic conference. Of course, it was a great pleasure to hear Professor Sriram talking about all the sustainability aspects. And now I'll move on to another slightly separate topic area, which is biomaterials. So let me first share my slides, and I just wanted to ensure I don't run too long. Until when do I have this talk session? I know it's 11:14 here. Is it a half an hour?
Yes, half an hour.
Okay, and that's excluding.
And then there will be questions.
Okay, brilliant. Thank you so much. I'll share my screen now. I hope you're able to see my screen.
We see you have good holidays.
Okay. Is this now visible?
Yes, that's great.
Fantastic. So as Professor Mitchell mentioned, I will talk about sustainable biomaterials of bacterial origin and their use in biomedical and environmental applications. So I think the first question that I would like to answer before you query me on this, why bacteria? So the main thing that I found as a material scientist was the fact that we all look for green, natural polymers. We want to use them for a variety of applications, environmentally friendly, packaging. I used mainly for medical applications. But there is a great issue about the repeatability or their properties changing depending on where this particular natural polymer has been isolated from. So just as an example, chitosan is a very commonly used biomaterial obtained from prawn shells. However, if the prawn has been grown in, say, Saudi Arabia versus in England, we will see a very different monomer content, molecular weight, etc., which therefore makes it a different material, really. So being my original PhD was in biochemistry, and I thought, well, if we do a very controlled bacterial fermentation, it is almost like a synthetic polymer. And we can control exactly the conditions like dissolved oxygen tension, the pH, the temperature, the substrate that is used. And then we get a polymer which is absolutely the same every single time we produced it. So this is why I was inspired to use bacterial fermentation as a source of natural polymers. So let me just take you through my journey. It started a very long time ago. Like Professor Mitchell mentioned, I've been working on these polymers for perhaps 24 years now. You can see the types of polymers that I have been working on. Polyhydroxyalkanoates have been my focus. We have also started working on bacterial cellulose. Gamma polyglutamic acid is something I've touched upon. And then alginate, which you can get from seaweed as well, I've started producing using bacterial fermentation. Oops, it doesn't let me change slides. So let me end show and go back to my slides. Okay. There we are. So these are the particular class of or type of polymers that have been working on the most, has been the focus in my group. These are called polyhydroxyalkanoates. As you can see from the structure, this is a polyester, and also it is a very stereospecific polymer. Another advantage of using bacteria, because if you want to synthesize these polymers to get a absolutely stereospecific polymer will be quite a difficult task. I divide, or the PHA world divides PHAs into two main types, the short chain length PHAs and the medium chain length PHAs. This is really governed by the monomer chain length. So if you have C4 to C5 monomer chain length, we refer to them as short chain length polyhydroxyalkanoates, and these are normally hard and brittle in nature. And then we have the medium chain length PHAs, where the monomer chain length goes from C6 to about C16. What is amazing about this family of polymers, and perhaps why I've been working on them for a very long time, is the fact that they are degradable in the soil. They are degradable in the marine environment, very unusually, that both environments this polymer is degradable in. And lastly, and not the least, these are also resorbable in the human body and highly biocompatible. I haven't found a single type of tissue that wouldn't grow on these polymers. Another very nice feature is the fact that, as you can see in the structure, the R1, R2, and the X values can vary. So what you're really looking at is a family of polymers rather than one polymer, one property. So depending on your needs, you can mix and match, you can choose one of them, you can even get copolymers made by the bacteria. So really the choice is immense. Another property that's wonderful about these is the fact that they degrade by surface degradation. So if you're making a structure out of these polymers, they don't crumble suddenly. They actually degrade like an onion peeling, and therefore you have stable structures which are gradually degrading away. And in the context of many applications, that's a very important property. So moving on, this is how I produce it. So since I moved to Sheffield in 2019, I have scaled up the production of these polymers. And I'm sure you will all appreciate that in order to be able to use bioplastics in a big way, we really have to scale it up. We have to reduce the costs entailed with these polymers. So this was my first step forward. This is a 30-litre fermenter that we have in Sheffield in a pilot plant, and that's what I use currently. So when I started many years ago, I looked at these polymers from a medical point of view. And I have to point out that in the medical world, there is not much emphasis on sustainability at the moment. We look at sustainability for packaging. We look at, like we just heard, in food area, in textiles, in construction work. But in medical arena, we don't really think about that. And I think it's high time we did. And this was one of my main thought processes when I started working on these, is to look at sustainable polymers for medical applications. And the first one I looked at was the polyhydroxybutyrate, which is generally produced by what are called as gram-negative bacteria. These bacteria have a lot of immunogenic materials like the lipopolysaccharides, which is not present in gram-positive bacteria. And my thought process was, if I want to use it for a medical application, I don't want immunogenic materials in that particular product. So why not start with a bacteria that does not have that immunogen? And therefore, I started producing these polymers in gram-positive bacteria. And this is a trend that has now been picked up by the industry, and they are now beginning to produce these using gram-positive bacteria as well. So poly-3-hydroxybutyrate, one of the most well-known polyhydroxyalkanoates, you can see it's a high melting polymer with a reasonably stiff nature. So the Young's modulus value is quite high, 1.7 gigapascal, which is quite a good value. And this is why I used and chose this polymer for a variety of applications. The other type of polyhydroxyalkanoate family, as I mentioned, is the soft and elastomeric medium chain-length polyhydroxyalkanoates. And I knew I couldn't just deal with the stiff and the hard ones. So I went forward in the production of the medium chain-length ones as well. And unfortunately, I can't yet produce them using gram-positive bacteria, but this is a thing in my diary to do before I finish my academic career. But at the moment, I use Pseudomonas, which is a gram-negative bacteria, but I ensure when I use it for medical applications, the lipopolysaccharide levels are much, much lower than the FDA-approved levels for medical devices. This is a typical medium chain-length polymer that I produce in my lab, and you can see it is low melting and its Young's modulus is quite low. But if you look at its elongation at break, you will see how amazingly elastomeric this polymer is, about 1200% elongation at break. This is a typical fermentation profile. I wouldn't go through all the details, but this tells you that we can control the process very, very closely. The dissolved oxygen tension, the polymer yield, the pH, the nitrogen, the biomass, everything can be controlled very, very closely. And this is a typical medium chain-length PHA that we have scaled up at Sheffield, where we can now almost produce a kilogram, which I'm really happy about, because now we can move on and really look at real products, both medical and environmentally friendly green products using this elastomeric polymer. We've done a similar task with the short chain length PHB as well, and hope to take these forward very soon. We always make sure we chemically characterize the polymers that we produce, because being a fermentation, we need to ensure that the material is exactly what we want. So here's an example of an FTIR spectrum, NMR spectrum, and also the molecular weight, as you will all appreciate, of any material is crucial for its property. We ensure and we check using gel permeation chromatography that we have the same molecular weight, the MW, the MN, the weight average, and the number average remains the same. Otherwise, it's a different polymer, completely different polymer. It might be chemically the same, molecular weight being different, as all of you know as manufacturers, that it changes the total property of the polymer. The other polymer that I mentioned that we've scaled up is the poly-3-hydroxyoctanoate, go-3-hydroxydecanoate, again, low melting, about 53, and the elongation break is about 536. Young's modulus is low, 5.7 megapascals. So this is the elastomeric polymer that we use for a variety of applications. So what can we do with these polymers? I am happy to say that we can actually process these polymers with most traditional technologies and most recent technologies as well. So you can see we've generated porous structures, microspheres, gyrospun them into very fine aligned fibers. We can 3D print these polymers. We've made drug-eluting stents with them, nerve conduits with them. We can melt electrospin them and solution electrospin them, and we can create 3D molded porous structures with these polymers. So how do we use these structures? My main emphasis, which I'm gradually moving on with in Sheffield as well, is the emerging medical aspects of PHAs. Like I said, sustainability in medical applications has not been focused on, and I think it is a very important area that we need to look at green polymer usage that can be used for various medical applications. I do look at environmental applications as well, like packaging and coating, which I will come to towards the end of my talk. So everybody thinks, or at least surgeons get really afraid when I talk about bacterial polymers for medical applications. And then when I tell them the good news that this has been FDA cleared for a particular application, which is by a company called TIFA, which is a spin out of MIT, then they are rested and they want to talk to me further about these polymers. It's also been CE marked in Europe, and a particular type of PHA, which is P4HB. So what have I used them in terms of medical applications? I continue to widen my horizon, but at the moment I have used them for bone, cartilage, kidney, semi-artificial pancreas, skin, cardiac, drug delivery, drug-eluting stents, nerve conduits, and 3D disease modeling with a focus on cancer. So I'll start with an example with bone tissue engineering. Here we've looked at gyrospinning. This is in collaboration with UCL, Professor Mohan Ederisinghe. And here you can see that we've taken a mixture of poly-3-hydroxybutyrate and hydroxyapatite and then spun them or gyrated them to form really nicely aligned fibers. So this is just a video to show you how this process works. And very beautifully, you can see that these gyrated fibers are emerging from this cylinder with holes, which have been really engineered in order to produce a particular diameter of fibers. And this is how they look, beautifully aligned and porous. And we have now looked into putting bone cells, primary bone marrow cells on them. The cells actually love the substrate. We've looked at initial in vivo and being also animal friendly. We didn't start off with animals. We looked at using eggs, chicken eggs, where you can actually put them on a membrane. And this is called a CAM study. This was done in collaboration with Richard Orefo at the University of Southampton. And we found that the chick egg or the chicken that would emerge from this is healthy. We get total vascularization of the actual PHA substrate or the PHA composite that we put into this. And therefore, really speaking, we prove that under in vivo conditions, this particular composite is highly vascularizable and it is biocompatible as well. So this is just a histology data which tells us that the red indicates vascularization and the blue indicates collagen formation. And I hope you agree that this looks like it has done really well in terms of both issues. We then went in vivo, and here again, the first row, or you can see, is poly-3-hydroxybutyrate on its own. And then the next is the poly-3-hydroxybutyrate along with cells. So we're using partially cells in the therapy to regenerate bone. We have looked at then poly-3-hydroxybutyrate with hydroxyapatite, and then finally with, again, the composite with the STRO1 cells. And I hope you agree that it is the last column that you see that we have the high vascularization and collagen formation. So we can therefore really conclude that having the substrate along with the STRO1 cells is the best way forward. Like I said, we can 3D print this structure. So for bone tissue engineering, we've looked into 3D printing this polymer. This is the more elastomeric polymer that I mentioned that we have now 3D printed successfully. We have now begun to also 3D print poly-3-hydroxybutyrate in our laboratory quite successfully. So this is an example of the medium chain length PHA where we have printed them quite nicely. I must mention that we always check the biocompatibility, and here you can see the osteoblast, which is the bone cell lines, worked attached and grew really well on these structures, the 3D printed structures I showed you. And here are the cells, green indicating they're happy and growing, and red indicating they're dead. And I hope you agree there's lots of green and very little red there. Peripheral nerve tissue engineering is another area, and this is my collaboration with Professor John Haycock at University of Sheffield. Here we look at repairing nerves. And after an accident or due to disease, when nerves break or shatter, we lose functioning of that particular area. And we looked at peripheral nerves. Firstly, we can look at the central nervous system in future. And what we looked at was creating electrospun aligned fibers with PHAs to begin with, which would act as an internal fiber for a bridge that we were creating between two broken nerve ends. So it's like giving a pathway for the nerve regeneration. And so these aligned fibers would act as a material within the bridge that would further guide the nerve cells to grow within and or meet the other end of the broken nerve and hence regenerate the nerve. And what we found is that the PHAs were doing really well as compared to polycaprolactone, which is a commonly used synthetic polymer for this application. And this is just to show you that we did what is called an ex vivo assay, where we take a chick dorsal root ganglion and we cut it just as it's a model for nerve injury. And we put it on a tube, on the top of a tube, and have the fibers inside the tube. And we test whether the nerve fibers will regenerate and grow through the tube into these polymer fibers. And these colored fiber-like structures you see indicate that yes, they do really well. They grow through these fibers into long functional nerves. We've done in vivo tests as well. This is a preclinical test that we did with a group led by Professor Goena in University of Torino in Italy, and where we used empty nerve conduits. The surgeons remarked that these were one of the most suturable nerve conduits that they had ever worked with, which was my pleasure to hear. And the nerve repair, it was very, very good. And in the interest of time, I will go a bit faster now. But what I would like to say here, that the grasping test, which is the functional test of the nerve regeneration, was told us that within 9 weeks, the empty tube behaved or resulted in a result as good as an autograft, where we'd actually put a real nerve or stitched in a real nerve in the nerve gap. A fantastic result. Cardiac tissue engineering, again, another passion of that I really enjoy working in. This was a British Heart Foundation funded research, and we were trying to repair a heart after myocardial infarction or a heart attack. What happens after a heart attack is we develop scar tissue on our heart. And therefore, the scar tissue, which you can see in this figure, the blue region, is completely non-contractile, and the heart therefore becomes really not non-functional, but its function is heavily challenged. And our idea is to create a cardiac patch which will provide healthy cardiomyocytes to this scar region and regenerate it into a healthy heart. So we use stem cells, and we used these polyhydroxyalkanoate patches to try and deliver stem cells which had been differentiated into cardiomyocytes into the scar region. And the challenge here was, as you can see, the left-hand side, sorry, it's gone beyond. The left-hand side is iPSC, or an induced pluripotent stem cell-derived cardiomyocyte, and this is a real mature cardiomyocyte. And I hope you agree that one is highly anisotropic, which is the mature cardiomyocyte, and the iPSC-derived cardiomyocyte is not really as anisotropic. So the challenge was to use the material to really mature the cardiomyocyte and therefore make it highly functional. So this, we used melt electrospinning of the medium chain length PHA and created these patches. As you can see with an SEM, we had these long, thin anisotropic struts on the patch over which the cardiomyocytes grew and matured really well. And you can see in the histogram that the aspect ratio of the cardiomyocytes grown on these scaffolds were much higher than grown on a normal plastic. We looked at the functional properties like calcium transients. We also wanted vascularization, so we looked at endothelial cells to be grown on these scaffolds, and we then co-cultured both the cardiomyocytes and the endothelial cells. We patched an acellular patch onto a heart, and we were delighted to see that the heart really took these patches well. There was no immunological reaction. It was as if it was part of the heart, as you can see in this figure. We then went on to cell-laden patches, and again, the acceptance was amazing. We also are developing a multi-material cardiac patch, and I think I will skip this because of, in the interest of time, but quickly show you that we can really make multi-material patches with PHAs and alginate, where alginate encapsulates the cells. And hence I want to produce the alginate using bacterial fermentation. I quickly move on to another topic, which is very close to my heart, that is the development of antibacterial polymers. And I think the pandemic also made us realize that we need antiviral materials as well, and both would be great if they were sustainable. So this was a European project that we developed a lot of these materials. Unfortunately, because of time, I will skip these slides, but I would like to tell you that we did successfully produce, and we have published this work, and you hopefully, if you're interested, can look at our publications in this area. We can 3D print these as well. Again, really promising step forward that the composites can be 3D printed. This was hydroxyapatite doped with selenium and strontium. And you can see that the composite was had nicely distributed filler. We looked at antibacterial activity as well. I promised that we also worked with bacterial cellulose. So here we are. This is the cellulose pellicle. This is a pellicle which is extruded by glucon acetobacter xylanus that we produce routinely in my lab. Look at the lovely nanofibrillated structure that is produced by nature. And this is also highly biodegradable in the soil. We always look at the structures to ensure we have the right material, and we have created an antibacterial bacterial cellulose by chemical modification. This is also biocompatible and very useful for wound healing. We've done drug delivery. Again, lack of time, I can't go through the whole topic with you, but we have ensured that we can get very nice controlled release kinetics from the microspheres generated with poly-3-hydroxybutyrate. We've devised, or we have created, medical devices like biodegradable stents. And again, I will just briefly show you, here is a stent manufactured using PHAs that were produced in a particular European proposal or project, ReBioStent. We've created 3D disease models. Again, these need to be sustainable. They are 3D. They help us not to use too many animals, so also animal friendly. And we tried to mimic breast cancer, which is a hard form of the cancer. And we really got structures of breast cancer cells, which, as you can see, look like grapes and beautifully mimic the breast cancer cells in their native environment. And hopefully we can therefore use them for drug testing rather than using animals for drug testing. Similarly, we've looked at colon cancer as well. And lastly, and not the least, I'll finish with my first venture where I'm looking at green coatings for PHAs and bacterial cellulose. This is a currently ongoing European project, which we finish soon, called Eco-Funco. Here, we're looking at extracts from a variety of sources, proteins, cutin, polysaccharides, polyphenols, carotenoids, fatty acids, and then looking at coatings on cellulosic and plastic-based substrates. So I wouldn't have time again to go through the details of this, but bacterial cellulose and PHAs are being looked at, green coatings on a variety of materials, including some antibacterial or antimicrobial properties. So I will conclude my talk today by saying that, of course, polyhydroxyalkanoids are an emerging class of biodegradable and biocompatible polymers of natural origin. And I think they have huge potential in both biomedical and eco-friendly applications. I have used them for hard and soft tissue engineering, as I mentioned to you. Bacterial cellulose is yet another natural polymer with huge potentials for biomedical applications and for green and eco-friendly applications. I'd love to thank my group, my key scientists, my collaborators, and of course, the funding bodies that allowed all this to happen. And I thank you all for your attention. Thank you.
Thank you very much for an impressive array of achievements. Congratulations on all of this work. And now we have a few minutes for questions. And I wonder if I could start by asking something you mentioned right at the beginning, but you never mentioned again, but that's fine. It's not was that you said that with this particular class of polymers, these degrade in a marine environment.
Mm-hmm.
So do you think it's a reasonable, I mean, you didn't suggest this, I'm now thinking about how you use this information. Is it reasonable for people to think, if it degrades in the marine environment, we're just polluting the seas in another way, right? And so should we not think about anything degrading in the marine environment because it's effectively pollution, whatever it is?
I think maybe I have a slightly different perspective. I think we can't suddenly switch to a society where materials will not reach the ocean. Of course, I agree that that would be the best case scenario. But having things like even, I use a shampoo every day and they have little microspheres of non-degradable microplastics in them. And we can't suddenly say, okay, we don't need to really use this anymore. But having the alternative that can be added, which then will not pollute. In fact, I maybe have not mentioned this particular polymer. When it degrades, it produces natural metabolites that are present in bacteria, in most living organisms, because they are part of the fatty acid biosynthetic pathway, the beta oxidation pathway. So ultimately, you're producing food in the environment. So if we can go that way, I think it's not really polluting the sea, but creating a nutrient source for the sea. So I would see it in that way. And switching to a society where nothing reaches the ocean, I think is a long way off. And this is a nice medium, a nice compromise, shall I, if I can say, put it that way.
Yes. Of course, it was in 1950 that we all agreed not to pollute the oceans.
Yeah.
So we're taking a long time to get there.
Yes.
So other questions? Any questions online, Renato?
Yes.
I can see a question here, if I may answer the question.
Yes, we have a question online.
So the question here is about how do we do it's about the CAM experiment. So what we do is we create a scaffold, and then there is a chorioallantoic membrane, which is what the CA stands for, on top of the egg. And we put our scaffold on top of that membrane. And if anything cytotoxic is eluting from this particular material, then the chick will not be able to develop, right? And so what we ensure is we look at whether the chick develops nicely in such a egg when it's incubated. And the other thing we look at is the chorioallantoic membrane is highly vascularized in a natural egg, a chick egg, or a hen egg, which is developing. Does that happen as well with the scaffold? Is the scaffold vascularized? And with tissue engineering applications, this is a challenge, which is why perhaps we can't make a huge structure for replacing tissues, because the central core of that scaffold does not get vascularized easily. So a challenge is to create material that gets vascularized well, and that is the other test we do. So it's not that we are incorporating the material in the egg, we are using it as an in vivo environment to check the feasibility of this material or the biocompatibility of this material. Does that answer your question? Great, thank you.
Yes, right, thank you for that question. While we're waiting for other questions, at one point during your presentation, you said that the particular fibers that you were using, I can't now remember what the particular problem was, but were better than similar fibers produced from polycaprolactone. Could you just indicate why this was the case? Is it the mechanical properties? Is it chemical, or is it the some details of the polymer?
Yes, absolutely. I think a very relevant question, because polycaprolactone is a very well used polymer. First thing, of course, I think in terms of my lecture, I move towards polyhydroxyalkanoates versus a PCL is because of the sustainability. It's not a synthetic polymer. Why the cells prefer the polyhydroxyalkanoates versus the PCL, there could be many reasons. One of them could be the surface structure. So we have in the PHAs, we have the alkyl group sticking out versus the polycaprolactone surface. And when we look at the affinity of these cells towards the polycaprolactone versus the polyhydroxyalkanoates, they seem to prefer the surface of these fibers. So it could be that the chemical interaction between the integrin moieties that actually lead to the attachment of cells to materials is better. And there could be certain proteins that get attracted to the surface of these polymers and not to polycaprolactone, and then enhance the attachment. So and this is something I haven't researched, so not something that I can say I've done the proteomics and seen what is causing this difference between PCL and P3HB and P3HO blends. But this would be my guess, that it is the chemical interaction between the integrins, which are the receptors for the attachment, and these particular polymer types. And of course, the actual diameter of the fibers also make a huge difference. And although we tried to keep the same diameters between PCL and the PHAs, sometimes you cannot achieve exactly the same diameter, and that might also affect this process.
Okay. Any other questions? I don't think there's anybody online. So a final question. We have a couple of minutes left for questions. One of the things when I look at tissue engineering, maybe we all have the same view, is that this is a wonderful concept. It seems very simple in its application, but in actual fact, it's never really quite made it over the hill into providing regular therapies. Could you say something about, you describe lots of aspects of the work you've done, whether these are moving closer to the situation where these will become readily available products or readily available therapies?
Yes, I think first product that I can think of that can really go into the market is the nerve conduits that we produce.
Yes.
Because these are very simple to manufacture the way we produce them. And as you've seen from the preclinical work that we've done, that it is really very, very efficient. And the surgeons seem to find it very suturable, which is very important at the moment. Without taking names, the nerve conduits that are available to surgeons aren't as suturable as they would like them to be. They don't have an alternative, and that's what they use. So I think that is the first product that is easy, simple, and can be taken to the market very easily. The other product that is very close is the cardiac patch, but the acellular version, because as soon as you bring in cells, it becomes the medical regulatory approval becomes quite a difficult pathway. I hope with the current corona pandemic, we've seen that this pathway can be shortened, and I hope it inspires us to shorten this pathway, but it can go 10 years sometimes. So the acellular patch would be my next product that I think we could take to the clinic easily.
Okay, thank you very much. So thank you very much for accepting our invitation. Thanks very much for spending some of your holiday time
Thank you.
with us today. Enjoy the celebrations and the party if you're having something later on. But we thank you, and we hope to see
Thank you so much.
see you again sometime, maybe in person.
Yes,
Thank you.
Absolutely. I look forward to that, and thank you
Right,
for.
so now we move on to the next keynote lecture, which is from Professor Artur Mateus from the Center for Rapid and Sustainable Product Development. He's a mechanical engineer by training, but very talented in all sorts of ways. And today he's going to be talking about circular seas, the great challenge for plastics.
Este.
Exatamente. Acho que é esse. É isto, né?
É. Acho que sim.
Então, só fazer o seguinte.
Good morning to everyone, those that are here in the center and those that are online. Thank you for your nice words, Professor Mitchell. And I will make now a presentation focus on a project that we are running, and also in a challenge that we have regarding the plastics in the sea. Most of them are not degradable, as we listened in the last communication. So this project, named Circular Seas, is a European project in an Atlantic area. We have the Cork Institute, the University of Plymouth, La Rochelle in France,
Larticat in Spain and also Vigo, and here in Portugal we are the key, the key of the network. This project have several activities, and one of the activity is to try to capture the plastic from the sea and try to transform it in products for maritime industries. Those that are related to fishing, those that are related with tourism, those are related with sports, and we believe that the key thing for a turnkey solution is to transform these plastics in value products in a value way, giving value to this plastic that is in a very, how can I say, a very bad environment, because the salt and all the things. Here I show some few products that could be made in plastic by using, okay, I didn't mention the target technology for transforming the plastic is a digital manufacturing technology known by additive manufacturing. So here I could show some products from others, mainly whole or close to whole are produced in plastic that didn't came from the sea. Only the shoes the shoes that I show here are made from plastic from the sea, and the reason is because it's not easy to transform something that have a lot of contaminants and salt and degradation in a product, a premium product or a premium material to be transformed by, what can I say, a premium technology. So we look to the 3D printing techniques, and there are several, those that are based on vat polymerization, material jetting, binder jetting, powder bed fusion, among others, and also the one that we choose for this transformation that is material extrusion, mainly thermoplastic material extrusion. A lot of plastics that are in the sea are those that we use every day, and mainly are thermoplastics, and some are thermosets. Even some that are thermoplastics are close to impossible to transform by melting, because they have a lot of degradation. So in some situations we need to use them as filler instead as the main material. The extrusion process have some challenges. I don't know if you are used to use this kind of technologies in your work or in your house, but these technologies are very sensitive to the quality of the plastic and the shape of the raw material. So I put here, or I present here, the common aspect of the raw material that came in filaments, usually 1.75 millimeters or 3 millimeters, and the extruder is very sensitive to the dimension of the diameter of this filament. So it's quite a big challenge to transform that plastic that came from the sea. First is a challenge to collect the plastic, then is a challenge to wash the plastic, then is a challenge to remove the contaminants and the impurities and other things. And of course, by the end, we need to have an homogeneous material
in order to work well with this kind and specific technologies that use filaments. In my, I have some experience in these processes, and even the virgin material, the raw material, have some problems when do not fit the very specific specifications. So also we have here, I show here an extruder to make this kind of filaments, and one key station or point of this process is to keep the dimension in around 175 if you are looking for 175, and not more or less than 10% in dimension and diameter. So even for very good materials and new materials, is not easy to keep these dimensions. Then we have a lot of other challenges regarding the process itself. I show here some of these like problems or challenges that are related with the several things. One is the first layer. The other one is to keep or to select the correct throughput, and because it's layer by layer. Also, if we have shrinkage, the layers start to can I say delaminate from the bottom. Also, if we have impurities, the nozzle we will block it. There are a lot of challenges to deal with the technology when we look to the common extruders. I show here some parts, some photos of part that we are doing now, but in a big scale, and really to deal with these difficulties of the small scale extruders, we are really look to use the plastic that came from the sea, or the compound that we could make from the plastic from the sea in big extruders, to avoid one step, that is to make the filament, because we know the filament is a big issue for the process, and to incorporate also fillers to keep to try to keep the shrinkage low. That way, also thinking about big, we could deal with the big quantities that we have in the sea, and also some parts of plastics that will not work as a binder but as a filler, because are a lot of degradation. So if we have a big extruder with a big nozzle compared to this, like 10 to 20 millimeters, we could pass through this nozzle some chips that are not melted, and they pass through. So the idea really is to small scale processes, but to big scale processes. And okay, and really this is our turnkey solution for this, turning the, really this is not perhaps so good for some, in some perspective, because we are preparing compound from the sea, plastic from the sea, and we are delivering again to the sea. But in terms of applications, so our application, we look around to see where could we apply in a valued way this kind of plastic, because for most people the plastic have no value. This plastic have no value because so much processing that we need to do to achieve a raw material. I don't know if you know what are these. These are master prototypes to making boats, to making, let's say, to making molds
or both. Usually, and this is this is nearby in Figueira da Foz. And what we are trying to do, and I think that we achieve that in the next few months, is to produce the master in thermoplastic, because we will use a massive quantity of plastic to produce the near net shape master prototypes, and then by the end of the life of this tool, this prototype, we could reuse it again, because it's a question to mill and to put again in the extruder. So for this work, we collected from the sea more or less, for the case study, 1 ton of PP, PE, and PAT that there are the common plastics or in the sea. Also, and these are some images, also thinking that PP and PE are semi-crystalline plastics and have a big shrinkage, that is a very challenging problem to make good parts. Why not use the calcium carbonate from shells that came from the food industry and put them in the compound? That way, if you increase with high quantity, we could decrease the quantity of plastic, and of course, if we have less plastic, we have less shrinkage and warpage. Is a consequence. The case study that we will put in place, because we are putting in place, it's a catamaran, a small one, 3 meters. It's for 2 people to go around to fish, and this is this yellow part is the floating, and the idea is to put the catamaran over our car and go to fishing, and then to the same. I'm breaking all the things. Okay, the catamaran, and we will do by extrusion and then milling a catamaran with a compound produced with polyethylene or polypropylene with a carbonate from the shells, trying to keep low the shrinkage, and this master prototype with a low to produce the floating part. This is made with the participation of Scale Oceans, that is a company nearby in Figueira da Foz, and this will be an electric catamaran. And the way, or the way to produce this is to grind, wash, micronize, and then combine and pass through. Could be a co-rotating extruded as a way to homogenize the material, and also to put the filler inside and to create a compound. This is not the catamaran, but this is the way we will produce in the shortly. Will be in this month. So this is another example, but we will do it in this 3D printer that is a little bit bigger than those that we are at our home. The extruder and the system for controlling was produced in the project with Periplast, and here we have a lot of development to do, but we already made a lot of progress. Oh. Okay, I think this is a movie. This is quite slow. We take perhaps 24 hours, 10 hours to extrude perhaps 150 kilograms. So it's very easy to have a mold that consumes 200 kilograms. For instance, for this floating part of catamaran is expected to need the need of 150 kilograms of compound, even, and the part will be hollow. These are some problems that we know that we will have, and also some ideas to avoid to try to reduce these problems. One, of course, is warpage. Everyone knows in 3D printing, the first layer is a key layer, and others also, okay, but the first one is a key layer to start the process well. And to do that, we need to glue very well the part to the platform. So we use here a clever solution to fix the part to the platform, because the plastic passed through the holes, and then we need to cut. So also a challenge is that we don't have really, what can I say, engineering plastics, amorphous plastics as ABS. So we have a lot of PP and PE that have a big shrinkage, and we'll try to keep the shrinkage low, adding calcium carbonate to make the pellets compound. These are just to show to you the worst part. It was made in a tire as a filler and polypropylene as the binder, and the other part that seems very good, it is made by ABS. The difference between those is that the PP have a very bigger shrinkage compared to ABS, perhaps 4 or 5 times more. But we will not do it by using amorphous materials. Mainly, we will use it by using semi-crystalline materials, and this is really a challenge. So these are some details to mix together the materials we use. Co-rotating extruder. Here we see Arthur, that is in my front, to making some materials in the extruder. The way is to put the material that came from the sea after smash it in the extruder, and the side feeders will feed the extruder with the fillers. So I think I'm ending my presentation, but the idea that I want to keep in mind is that for the rescue of a lot of big quantity of plastic from the sea, we need to look and see if we found an economical way to guarantee this. That also is a way for sustainability, because if we use that in components that make sense, in the quantity that makes sense, perhaps then could be easier to motivate people to use the material and to capture the material from the sea. I need to thank to all the team in several projects that work in this the rest and others from outside, also to the project Circular Seas, the escalations and LCR companies, and also an association in the south of Portugal that capture a lot of plastic from the sea and make also this possible. Thank you very much.
Thank you very much, Artur. Now, some time for questions.
Oh, okay.
You need to stay there, so you're on camera.
I was thinking that you can hear.
So, questions or comments?
For the case of catamaran, you will use the 3 types of materials, or you will select just one type and use it? The 3 of them?
We will look to one, but the idea we have a big quantity of polypropylene and polyethylene. Okay, is like then we need to look to the small shrinkage after first experiments, but for sure that we will have bigger shrinkage. However, the part, the shape of the part, and also the way we put it in fabrication need to be considered to reduce that. But I think that will be polyethylene. We have a lot of quantity.
Thank you. Any questions online, Ronaldo? No or yes?
No.
No. So it's only available in black?
You know that perhaps in como é que chama cinza? In gray, because if you put a lot of filler,
Yes.
filler is white,
Yes.
then we could make that in a different color. We will avoid to paint because the recyclability of the material in the end. But it's like Ford said some years ago, you could choose the color of your car, but if it is black.
Yep. Any other questions?
Sorry, I can't seem to get the chat to work. So can I just ask a
Yes,
question directly? Just to ask, I love the way you are doing your innovative printing with the plastics from the ocean. And you asked the question about bioplastics not being reality yet, or not being available in a big scale. Have you ever tried manufacturing things using the available bioplastics, like, you know, PLLA or, you know, the like? No, well, not PLLA from the synthetic route, but natural origin, or any other bioplastic, like the PHAs, for example, PHB.
Yes. We have a lot of work in by using those plastics, PCL and the PLA, and also putting some bio fibers from several resources. PLA is a good thermoplastic for 3D printing because they have a very high range of processability, and okay, that also could be a choice. But because we are trying to capture and use the plastic from the sea, in this particular case, we are using the material that are most in more quantity in the sea, that are really PP and the polyethylene and PHE. Okay, work with the PLA and all other materials is also a strategy that we have.
I see. Thank you. And PHAs, are they on your agenda at all?
The
PHA, PHB, maybe?
PHA, PHB. Okay, that came from bacteria also.
Yes,
yeah. Those are also in our roadmap. However, I could say, I don't know if in the center some work with the PHA or PHB, but is really interesting. And the properties are, as far I know, as quite close to some plastic of engineering. So it's very interesting. I don't know if you work with PHA, PHV, because if you work with PHA, PHV, it could be a good way to collaborate with you.
Yes, that's why I was asking. I will get in touch.
Okay, yeah, okay, yeah. Because we really in the past I see some
some few materials in the next fair in Frankfurt, but never saw again a supplier to make some tests.
Yes.
Okay, thank you.
Thank you.
Other questions, comments? Anybody online, Renata? Okay, so thank you very much, Arthur.
Thank you.
All right, now we move on to two contributed presentations. The first is from Ivan Galval from the Institute Polytechnic of Lisbon, and he's going to talk about the production of hybrid structures by solid state welding. So over to you, Ivan.
Oh, thank you very much, Mr. Chairman. As you said, my name is Ivan Galvão. I'm professor in the Polytechnic Institute of Lisbon and researcher in the University of Coimbra. This work, production of hybrid structures by solid-state welding, was developed by a research team, which is composed of members from 3 different institutions, namely the Polytechnic Institute of Lisbon, the University of Coimbra, and the Polytechnic Institute of Leiria. And now I am going to present this work by stressing our main methodological options, but also our main results and conclusions. And this is, sorry, I'm trying to go forward. Okay. This is the outline of our presentation that will begin with a brief introduction on dissimilar welding. Then I'm going to refer the objective of this work, but also the experimental procedure that was followed by us. At the second stage of this presentation, I'm going to present you the main results of our work with a special focus on the morphology, chemical composition, and mechanical properties of the welds. And finally, I'm going to do a brief discussion on our main results and taking our main conclusions. So, regarding the hybrid structures, the production of this kind of structures, it is especially important for several sectors, because these structures enable to produce new engineering solutions that combine the specific properties of different materials. And for example, for the transportation sector, we have high interest to join, for example, aluminum and carbon steel, because this will enable to reduce the cost, but also the weight of the vehicles, and we can produce more efficient vehicles. And as a consequence of this, we can achieve a more sustainable sector with a lower carbon footprint. But we have also interest to join other materials such as copper and stainless steel, because we can couple the properties of copper, for example, the thermal and electrical conductivity, with the corrosion resistance of the stainless steel. However, we have a big problem, which is the limitation of the conventional fusion welding technologies for joining these materials. So we have to look to a different family of processes, which are the solid-state technologies, the solid-state welding technologies. And here in this slide, I'm presenting you 2 different solid-state processes, explosion welding and friction-stir spot welding. In explosion welding, we take part of the controlled detonation of an explosive mixture over the surface of a top plate. And as a result of this detonation, we will have the projection of this plate that we call flyer plate over the surface of a stationary base plate. And because of the couple effect of the pressure and the temperature at the interface, we will have the joining of the materials, and good bonding conditions will be achieved through this process. And here you can see some of the main parameters of this process: the detonation velocity, the collision point velocity, which is the velocity at which the welding occurs, the projection velocity, also called impact velocity, and the initial distance between the plates that allows the acceleration of the flyer plate, and we call this distance standoff distance. This is the beta angle, the dynamic angle. Regarding the other process, friction-stir spot welding is a punctal welding technology. It is a derivative process from friction-stir welding, and it makes use of a non-consumable rotating tool that performs in the materials to join. This tool will produce, by the contact with the material, will produce the heating and the plastic deformation of the material. So the coupled effect of heating and plastic deformation will enable the production of the joint at the interface of the materials. And in this process, we can use two different types of tools, because the tool is the main part of the process. We can use a conventional tool composed of two parts, a larger part that is the shoulder and a smaller part that is the pin, but we can also use a non-conventional tool that it is only composed of the shoulder. These tools have no pin. So this tool will act in the material for a specific time, and this time is the dwell time, that is other parameter of this process. So based on these processes, we developed this work that was aimed to test the application of these two processes, explosion welding and friction-stir spot welding, for joining materials with very different properties, physical properties. And in this case, we studied copper and stainless steel. Our analysis was especially focused on the morphology, the chemical composition, and the mechanical properties of the welds, and we followed an experimental approach. In terms of the procedure that we followed, we produced two series of welds, a series of explosion welds and a series of welds produced by friction-stir spot welding. For the welds produced by explosion welding, we used copper and stainless steel under the form of plates with a thickness of 3 millimeters, and we produced welds by positioning the materials in different ways. Some welds were produced by positioning copper as the top plate, the flyer plate, the one that is projected over the other, but we also produced welds with the reverse positioning of the plates. In all the welds, the explosive mixture was AMPHO, and the initial distance between the plates was 4.5 millimeters. For the other process, we actually used the same materials, but 1 millimeter thick plates. These plates were a little bit thinner than for the other welds. We also test the alternative positioning of the plates. So some welds were produced with copper as the top plate, and some welds were produced with stainless steel as the top plate. Regarding the rotational speed, which is one of the most important parameters for this process, we arranged it between 870 rotations per minute and 1,500 rotations per minute. Regarding the dwell time, we arranged it among 20 and 60 seconds. Regarding the tool that we used, this tool was a pinless tool, and we test two different shoulder diameters, 10 and 12 millimeters. All the welds after their production were subjected to characterization by optical microscopy, SEM, EDS, and hardness testing. This was our experimental procedure. So, in terms of the results, here we can see micrographs of the interface of the longitudinal cross-section of welds produced by explosion welding. And these micrographs concern the one at the left side to a weld produced with a stainless steel as the top plate, the flyer plate. But the other one was produced with the reverse positioning of the plate. So in this case, the copper was the flyer plate. But when we look to both micrographs, we can see that in both cases, we had the formation of a wavy interface. This is an interface composed of well-defined waves. And this is a very specific morphology of explosion welding. And we cannot see any kind of material discontinuity between the materials. So good bonding conditions were achieved for both base material positioning. We can also see some small zones of interaction. And we call these zones interaction zones because we can see that the morphology is slightly different from the morphology of the welded materials, the stainless steel and the copper in both cases. Then we look to the interface of the welds produced with the other process, the welds produced by friction stir spot welding. And we have a very big difference when we compared both processes. And this difference was that by using this process, good welds were only achieved when stainless steel was positioned as the top plate. For the other case, no good conditions were achieved. So good welds were only produced by positioning stainless steel and as the top plate and copper as the bottom plate. And in this case, we can see a different morphology from the explosion welds. So instead of a wavy interface, we have a very flat interface, but as we observed for the other welds, we have no material discontinuities between stainless steel and copper. So we can also say that good bonding conditions were achieved when this base material positioning was used for friction stir spot welding. So then we tried to look with a further detail to the morphology of the interface, especially for the features formed at the interface. And here in this micrograph of an explosion weld, we can see a feature which corresponds to an interaction zone. And this interaction zone was formed in a vortex region. And the vortex regions are the zones in explosion welding where the highest peak temperatures are achieved. And sometimes we have some melting in these regions, although explosion welding is a solid state process. For the other case, as I said before, we had no well-defined waves for the friction stir spot welding because this is a specific morphology of the other process, but we can see some interpenetration of the materials with a very high magnification. So we called it micro-interlocking. We can say that both the micro-interlocking in friction stir spot welding and the wavy morphology in explosion welding had a very important impact on the welding conditions. And because of this, good welding conditions, good bond conditions were achieved. We also tried to understand the chemical composition of the interaction zones formed at the interface of the explosion welds. And here we have the EDS maps obtained in these zones. We have only the EDS maps of copper and iron, and we can see that these zones are composed of these two elements. But these zones are also composed of the alloy elements of the stainless steel, such as the chromium and the nickel. So we can see that these zones present a hybrid chemical composition, which shows some interaction of the materials during the welding process, but this interaction was very localized in very small zones. We also tried to understand the chemical composition of the interface for the friction stir spot welds, and we did this by EDS. We did an EDS scan across the thickness, across the interface of these welds, and we did not see a sharp transition between both materials. We have some evolution in iron and copper, so we can say that we have the formation of a very thin region with a hybrid chemical composition also in these welds. However, before taking very solid conclusions about the phenomena supporting these results, we still need to analyze these results further. For example, for discarding some limitations of the techniques that we are using. So our next step will be to analyze these results deeper in terms of the experiments that we have to do. Finally, regarding the explosion welds, we try to understand the hardness of the interaction zones. And contrary to what happens for other couples of materials, we did not have the formation of brittle structures. And brittle structures are one of the main problems in dissimilar welding. But in this case, we had not the formation of these structures, and we can see that the hardness of the interaction zone is much lower than the hardness of the deformed stainless steel. The original hardness of stainless steel was about 140 Vickers, and after the deformation, we can reach a value of about 440 Vickers. This also happened to copper, but the hardening in copper was a little bit lower. But the main result from this analysis was that brittle structures were not formed in the vortex zones, in the interaction zones of the explosion welds. And this is an important result. So in terms of discussion of our results, we can say that explosion welding allowed the production of good welds by positioning both the copper as the flyer plate or the stainless steel as the flyer plate. So both base material positioning were effective for the production of good welding conditions, production of good welds. For frequency spot welding, the results were different, and we found that the material's positioning had a very strong effect on the welding conditions. And we think this happens because we have very different thermal conditions when we put the tool working with the copper or working with the stainless steel. And this is certainly related to the very different mechanical and physical properties of copper and stainless steel. As one of the main aspects to highlight from this work, we can say that the short time of explosion welding and the non-mixing in pinless frequency spot welding, yes, because we used frequency spot welding, but with a pinless tool, and these were the main aspects for preventing a strong interaction of materials. And this is good because in dissimilar welding, when we have a very strong interaction, we may have also the formation of material discontinuities. So, as the main conclusions of this work, we can say that the base materials positioning in the joint has a very strong effect on the similar frequency spot welding of copper and stainless steel, and that the use of a pinless tool prevents the mixing of the base materials in frequency spot welding and consequently the formation of material discontinuities. For the other process, for explosion welding, we saw that this process promotes the formation of wavy interfaces, but no brittle structures were formed at the interface of the joints. So, as a final statement for this presentation, I would like to say that although further research is still required, we can say that explosion welding and frequency spot welding have a very high potential to succeed in dissimilar welding of materials with quite different properties. And in this case, we saw it for copper and stainless steel. Thank you very much.
Thank you very much for interesting presentation. So we have a few minutes for questions. Could you just say, I found it very, in my mind, maybe my mind's not so well tuned to this topic, but what explosion welding actually involves? You're just banging the material into another material?
Yes, it's that we take part of the controlled detonation of an explosive over one of the plates, and this explosion will accelerate one of the plates and it will impact over the other. So the couple effect of the plastic deformation at the interface and even some heating will produce the joint. But yes, it takes part only the explosion.
Why doesn't it bounce?
Sorry?
Why doesn't it bounce? Well, as far as I can see, you're firing a plate at a plate that is on a substrate.
Yes.
And so why is it that this deformed material interface is formed as against the plate hitting it and bouncing off?
Yes. The plate at the interface, we will reach very high values of temperatures in some localized zones, and in terms of plastic deformation, it will be extreme. So we will have the involvement of both materials, and they join under the action of this impact.
So there is some threshold for the velocity that you need to
Yes.
you need to move it at.
Yes, we have to achieve a minimum in velocity, but we cannot exceed a maximum value because we have two cases. If you have a very slow velocity, we will not have enough plastic deformation and we will not obtain the weld. But if you have a situation of over velocity, so a very high velocity, we will have melting of all of the interface, and this will also promote the separation of the plates after the impact. So we have to avoid very low velocity, but also very high velocities, because in the case of having a very high velocity, we also have melting all over the interface, and this is very detrimental for the bonding conditions.
Could you give us some idea of what the velocities that are involved?
Yes, I would say that in average, we will have a velocity of 800 meters per second, 600 meters per second, more or less.
Yeah. Okay, thank you.
Thank you.
Other questions? Any questions online?
No.
Perhaps I could just ask another question. When you observed the fact that changing AB to BA didn't work in the friction welding.
Yes.
Did you explore any way of achieving the result you wanted by changing the thermal environment of the lower plate?
Yes, we are studying it at this moment, and we measure the temperature for both cases. And when we have the stainless steel as the top material, the temperature reached during the process is higher. And in our opinion, we can say that this is related to the very different thermal conductivity of copper and stainless steel. So when we have the copper as the top material, as the tool is working in this material, the heat will dissipate very quickly, and the heat will not be enough to produce good bonding conditions. So in the other case, when we have the stainless steel, as the thermal conductivity of this material is much lower than that of copper, we will keep the heat in the interface and the heating conditions will be better, and consequently this will result in better bonding conditions as well.
Yeah, okay, thank you. Another sort of question that came up, because I wasn't quite certain when you started what you're making these structures for.
Yes.
What's the application of these structures?
Yes.
So what is the thickness? Why do you need a big thickness of copper?
Yes, in this case, we are trying to solve the weldability problems. And for us, it is easier to weld plates with not very thin plates, okay? This was the reason for welding 3mm thick plates, not in terms of practical application, but at this moment, we still need to know all the aspects related to the weldability of these materials, and this was the reason that we are trying to use thicker plates, because in terms of the experiments, it's easier for us.
Yeah, okay, thank you. Renato, I'm looking at the chat number. It's the same, so there's no questions online?
Yeah,
no. Okay. So thank you very much.
Thank you
For your contribution to RESIM, and good luck with progressing the research, and thank you very much.
Thank you so much, and thank you all.
And this brings us to the last presentation of this morning. So apologies to Eva Silva for keeping you waiting, but she will talk about computational evaluation of sustainable water-cooled heat sinks manufactured by powder bed fusion. And she's from the University of Minho, also in Portugal.
Yeah, thank
So
you.
over to you, Eva.
For the introduction. and congratulations for this amazing conference. I'm going to share my screen. I think you are seeing, right?
Yes, you could put it in presentation mode. Yes, thank you.
Yeah. So my name is Eda Silva. I am from the University of Minho. I am a PhD student, and I am here to talk about computational evaluation of sustainable water-cooled sinks manufactured by powder bed fusion, which is an additive manufacturing technology. Previously, I need to mention that this work continues a work that was already published in a journal, so I will refer that later. First, I will do a brief introduction to the team, mentioning the main goal of this work, and then I will present the methodology and materials considered, as well as the main results, and a brief discussion and some conclusions of the work. So, as you may know, all electronic devices generate heat during their operation. So, by providing heat dissipation, a heat sink prevents overheating and plays a crucial role for temperature control. Heat sinks that work under forced convection can be cooled by air or water. In this case, we will study the heat sinks cooled by water. Nowadays, cooling techniques must also be improved, as the increase in electronic complexity generates more heat in more tiny components with more dimensional constraint enclosures. So, due to its geometric freedom and the capability to build internal channels and internal structures with higher total to area to volume ratio, additive manufacturing can be a useful way to produce heat sinks that outperform the thermal performance of the conventional ones, using less amount of raw materials and with less waste. So in this sense, the main goal of this study is to evaluate the performance of different water-cooled heat sinks to be produced by powder bed fusion with aluminum alloy, ALSE10Mg, via CFD analysis, reaching temperatures as low as possible and minimizing the heat emissions to air. To this, the compositional domain includes a water-cooled heat sink with main dimensions 50 per 50 per 50 cubic millimeter with a 4.5 millimeter shell, and we put some temperature and pressure sensors. We can see in the image of the place sector. The geometry was measured by applying body size operation, and depending on the heat sink model and the study, we consider tetrahedral as hexahedral elements with a size varied in a range between 0.5 and 1.5 millimeters. The total number of elements was the one which was converged with minimal computational effort, as you imagine. So solver settings were defined including material properties, the boundary conditions, and the initial values. Regarding the material properties, we consider the aluminum alloy ALSE10Mg, as I mentioned before, and in the previous work, we duly characterized this alloy. So the values that you see here for the specificity and thermoconductivity, wherever, they were previously experimental measured for this specific alloy produced in the specific machine. As boundary conditions, we consider an initial temperature of 20 degrees with the heat source temperature applied around the bottom of the model, like the bottom side, and at of 92 degrees, sorry, with an inlet water velocity of 1.22 meters per second, which means a Reynolds number of 12,500. So the results were captured 15 seconds on the respective sensors, so the temperature and the pressure drop. And here we have we consider the critical knowledge that we obtained in the previous study that I mentioned before, and we analyzed the influence of fins or pin thickness or diameter and spacing. So here we conclude that we can see that black is the fins, and the pins influence on its sink temperature. And on gray, we can see fins, and pins influence on pressure drop. So the main important parameters influence on its sink temperature, as you may know, for reducing the emissions to air. And we can see that for a lower temperature, which is this axis, sorry, yeah, here, which is this axis, we should have higher thickness and higher diameters. For pins spacing, the conclusion is similar. For lower temperatures, we should have bigger spacings, and here the spacing between the pins and the fins. And here in the orange line, we can see the baseline, which is a heat sink that was manufactured without any features inside the heat sink, so it's only a channel. And we can see that most of the times, is including some features, we can reduce the temperature and the pressure drop. So it's good to put these features to a better thermal performance. So after these conclusions, the same studies were done considering the best fins and pins heat sink reported on the previous study that I mentioned. So we consider pins with holes and fins here, and fins with a trapezoidal shape and also with holes. Here we comparing the simplest fins or pins, the results that I showed before. There was an improvement in the thermal performance up to 9.5%. So additive manufacturing design approaches are also advantages in these water-cooled heat sinks. Also, considering the potential of additive manufacturing technologies, we study lattice heat sinks with different unit cells with the same unit size. And among the model study, the cross-party heat sink, which is the lowest unit cell, is the one with the higher surface area to volume ratio. And for this reason, this was the best heat sink. And the results here were up to 18.5% better than the ones reported on the previous slide. After the analysis of water-cooled heat sinks, where we consider the height of 20 millimeters, a different study was carried out to understand what would be the weight of a previously optimized lattice air-cooled heat sink needed to reach the same temperature that was reached with water. I remember that was the temperature of 35.4 Celsius degrees, considering, of course, the same Reynolds number. So the results for this lattice heat sink, which is in the paper that I mentioned before, we have here the height that we need to achieve different temperatures, and we can see that with this heat sink, water cooled, and with lower height, we need, for the previous one, a height of 28.5 millimeters, so more material, more volume. So it's better to consider this approach, which is a micro-channel heat sink. Sorry. So this proves the advantages of applying additive manufacturing technologies, namely powder bed fusions, in the production of components for thermal management, whether in air or water cooling. In the case of water cooling, a smaller volume of material, as I mentioned, is needed to achieve the same thermal performance. So these make them more beneficial for teeny and sustainable enclosures. Concluding, the thermal performance of water-cooled heat sinks was conducted by CFD simulations, taking advantage of additive manufacturing freedom of design. Through a direct comparison of heat sink temperatures under the same boundary conditions, it was concluded that inclusion of small features inside the water-cooled heat sink is beneficial to improve the performance. The various heat sink designs presented in the study have equivalent weights and can be easily produced by powder bed fusion technologies with aluminum, reducing the amount of raw material and also reducing the amount of waste that is generated. in a single operation production, which is a very important point for sustainability. We don't need assembly steps. So therefore, additive manufacturing, it seems, have a great potential to be applied in efficient and sustainable thermal management systems and electronic enclosures. And thank you for listening.
Thank you very much for a clear, interesting presentation. We have time for a few questions. Perhaps I could just start by saying you emphasized at the end that it was good for sustainability to make a smaller heat exchanger, but you didn't say anything about the cost of the water cooling.
Yeah.
Where does the water cooling come from?
Sorry, I didn't listen.
Right. So at the end of your presentation, in one of the conclusions, you said that this was much better to have a more compact water cooling system because it used less material. But
Yeah.
you didn't say anything about where the water cooling comes from. And
Yeah,
what's the energy, what's the carbon footprint of the water cooling?
Yeah, actually, that was not an exercise of the study. We only studied the different designs to improve the performance. But as you may know, it works with a pump that puts water inside the microchannel, and we can cool down the system.
Yes, I agree it's easy to do, but I think if you're to advance that there's advantages for sustainability, then we need to consider the whole process.
Yeah.
And not just one part of it.
Yeah, of course.
And it may be that a larger system that uses air that could be used to that doesn't require any particular other activities could have a lower carbon footprint, but it's small, but it's very interesting work.
Yeah, that is another step of the study to do like
Yes,
a LCA
yes,
and LCC analysis of
yes.
both its things.
Other questions? Comments? I think we're all enthusiastic for lunch, probably. So, Eva, thank you very much for coming today and very much for your very clear presentation. So thank you.
Thank you.
So that concludes this morning's session. Thank you all for being here and for taking part, and for all of those who asked questions. We will restart at 1400 hours, 2 p.m. And my colleague, Dr. Joanna Coutinho, will be the chair of that session. Thank you.
Yeah, lunch. Well, yeah.
Ok, já está. Vais apresentar isto?
Não, não, não.
Isto
Vou
isto é outra
apresentar,
pessoa.
depois
Tá
vou
bem.
apresentar a Joana. Obrigada, Arthur. Hello, good afternoon. I'm Joana Coutinho, postdoctoral researcher here at CDRSP, and I'm very pleased to welcome you to this second session of RESIM 2022. This session will broadly be about natural resources, from forests and oceans to promote sustainability, while we also focus on the circular economy. Now it is with a huge pleasure and a great honor that we will receive our lecture, our plenary lecture, Dr. Joana Vieira from ForestWise, with a work entitled The Potential of Forest Products to Improve Sustainability. Please.
Precisa da vossa apresentação?
Sim.
Certo. Pronto, quando quiser, podes pôr a apresentação.
So good afternoon. Thank you, Joana, for the presentation. And I'll also like to thank Professor Mitchell for inviting ForestWise to give this talk about the potential of forest products to improve sustainability. So my talk and these afternoon talks are different from the ones in the morning. In the morning, we were talking about materials. Now we are talking about the source of these materials, and I will start by talking about the forest. So first of all, I will introduce my institution, ForestWise, because we are a collab. So this is a new entity. We started in 2010. So the first collabs were established in 2010. And the main objective of these collabs is to create directly and indirectly qualified scientific jobs in Portugal by implementing research activities and innovation oriented to create social and economic value. So our collab, ForestWise, which is the collaborative laboratory for integrated forest and fire management, has the aim to promote the integrated management of forest and fire through co-research activities, innovation, and knowledge and technology transferred in an unprecedented effort from business academies, from business companies, the academy, and public entities. So these are our associates, which are 15, and they are from these three groups. So we have public entities, we have the academy, and we also have business companies. So now to begin my presentation, I will have this brief introduction on the Portuguese forest. Then I'll talk about forest products, forest services, and the challenges that the forest sector is facing. So I don't know if you are aware, but the Portuguese forest represents 36% of our soil occupation. So this dark green mass that you see here is the forest, the Portuguese forest. So you see that we have these three main species. So although the Portuguese forest is 70% of native species, we still have 26% of eucalyptus and another 4% of other species. So the other main species of our forest are the cork oak, Quercus schuber, and maritime pine, Pinus pinaster. So these three species are very important to our economy. They represent alone just the forestry sector represented by these species. They represent 100,000 jobs, which is 4% of the Portuguese workforce, and 10% of the national exports, representing 5,927 million euros, which is 2% of our national gross domestic product. Just to have a notion of what this means, in the Europe of the 28, Portugal is the third economy with this percentage of the forestry importance in the economy. So above us, just Finland and Sweden present a higher percentage of the forestry sector in a GDP. Oh, yes, that's what I was just reinforcing. So these are our main forest products of our forests. So we are the third producer of this wood pulp. We are the second European producer of UWF paper, which is wood-free uncoated paper, and we are the world leader in the cork sector. So now that I have given this brief presentation about the forest sector in Portugal, I'm going to talk about how forests and forest products can help improve sustainability. So when we think about forest products, the first thing that comes to mind is, of course, wood. It's like inevitable to think about wood. So wood is a natural renewable resource, and we can use it as a material to replace other materials, improving sustainability. So one of the sectors that we talked about this morning was the construction sector. So the construction sector is responsible for 39% of the carbon dioxide emissions. So of course that this is not just from the building of the construction of the buildings, but it's also due to this operational energy that is related to electricity and gas, and to this indirectly to this embodied energy of the construction materials. But besides these emissions that are a problem of the construction sector, there's also another problem which is related to the global emissions, to the residues that this sector produces. So 25% of the global residues are from the construction sector. So one way to overcome this problem and try to make the construction sector more sustainable is by selecting construction materials with a lower embodied energy, select energy efficient materials, and also select biodegradable materials. So of course that wood could be one of the solutions for this problem, and one of the materials used to replace this with these other materials with a higher ecological footprint. So you see here the embodied energy of wood is 25 to 60% lower than other construction materials. Wood is also a natural insulation material with better thermal performance and is biodegradable, so it has less residues. So if we start incorporating wood in construction, replacing it by other materials, we will have a lower ecological footprint and a higher sustainability. This is an example of some wood products that can be incorporated in construction. So here we have this conglomerate, which is made out of cork. It's an insulation material. I'm pretty sure you are familiar with it due to its acoustic properties. And these are several types of compressed wood, laminated wood, that it's insulated for floors, for panels, and for the building envelope, just to the outside of the building. So we have already several options in the construction materials. So of course the forest is not just the tree, so it's not just the wood. There are other products besides wood in the forest that we can use to help improve our sustainability. And these are the non-wood forest products. So I already gave you an example of a non-wood forest product made out of cork, but there's also pine resin, mushrooms, nuts and berries, medicinal plants, and honey. All of these are non-wood forest products, and the incorporation of these products into biomaterials can help us improve sustainability. So I will start by talking about cork, which is, of course, the main staple of the Portuguese forestry economy. So it's the production of cork. And I'm pretty sure everyone knows that cork comes from the oak tree, that it's called Quercus tuber, so the cork oak. This is the distribution of the species, and you can see that there's this big blue dot in Portugal, which corresponds to the main distribution of the species. So it makes sense that Portugal is the biggest producer of cork and cork products, because of course we have this big presence of the species in our territory. Of course, that it's not just limited to Portugal. We have the species also in Spain and around the Mediterranean area. So the cork is this material. It's the bark of this oak tree. It is removed every 9 years. And because these trees have a longevity of around 200 years, we can have 15 to 80 harvests per tree. So it's really a sustainable product. Now, the first harvest is when a tree is 25 years or when its diameter is of 70 centimeters and 1.3 meters. But this first cork, this first harvest, it doesn't have the quality to produce these wine stops. Neither does the second time that you harvest. Just after the third time that you harvest the cork has the quality to make the wine stops. So all this other cork resulting from the first and the second harvest, and also the cork from some of these smaller branches, doesn't have quality to produce these wine stops, but it's used in other products. So you see here the cork, the high quality cork, and the extraction of the wine stops. But then you have these other wine stops, which are technical wine stops that are made with this conglomerate cork. So the industry takes these leftovers, these subproducts of making these high quality corks, they granulate the cork, and then they use that material to produce these other wine stops. So this is for the high quality cork. The other cork that has a lower quality, it's also granulated and used to make these two composites. So we have this first composite that it can be mixture with several materials, several different glues, can be mixed with rubber, and depending on what you mixed it with, you have a different product. So we can have these products that are, I mean, everyone knows this use of the cork industry. If you have come to Portugal, it's almost impossible not to see in all these tourist little shops products made out of cork. So it has a big utility there. So in the textile industry is as a design material, and also again as a construction material to produce this insulation material, to produce floors, to produce several things. So cork is a really versatile material. It's not just used to make these wine stops. It's also used in space shuttles as an insulation material. So again, a very versatile product with different uses that can be used to help improve our sustainability. Just to give you an example of the cork sector in numbers, so Portugal is the world leader with 62.5% of the production of cork. In our country, we have 640 companies that produce cork or cork products with 8,343 direct workers, which corresponds to 1,016 million in exports. And from these exports, 25% are related to construction materials. So construction materials start also to have a big importance in this sector. So I've talked about two species in the construction materials. A lot of it's from eucalyptus and from pine, talked about cork, and now we are going to talk about another non-wood forest product, which is pine resin. So what you see here in this map is the distribution of pine trees, in this case, maritime pine and Aleppo pine, which is Pinus pinea, the two main species that are used for resin extraction in Portugal. These little triangles here represents the industries of the first and the second transformation of natural resin in Portugal. So we have a big sector that is distributed in the country. So this pine resin is extracted mainly from Pinus pinaster and Pinus pinea trees, but mostly from Pinus pinaster. So there are few trees that are already being resined in Pinus pinea, but traditionally it is Pinus pinaster maritime pine. It's the tree that it's used for this purpose. So this is a regulated activity. There are rules and norms to produce, to extract this pine resin. There's a period of extraction, which is from April through October, when the tree is physiologically active. So this resin that comes out of the pine, this is produced when a tree is under attack or when it suffers